And so we are going to go ahead and review lessons 1 through 6, the different topics that we talked about. So on your handout, you can see that the first thing we're going to do is talk a little bit about algebra and what we've learned about algebra so far. And so this is just a section for you to kind of jot down things that you want. We'll do some example problems, but if there are some things that stand out that you say that you know, things that you want to remember, go ahead and jot them in there. One of the first things I want to talk about is just reviewing the vocabulary that we discussed for algebra. So if we have something like 4x plus 3 equals 7, okay? So this we'll talk about vocab. X in this case is a variable, right? What about 4? What is that? Anybody remember? Good. That's the coefficient. Okay. What about 3? Good. 3 is a constant. It's also one of the two terms, right? And 4x is the other term. And addition is the operation. That's an E. Great. And this whole thing we call an algebraic expression. Okay, so those are some variable coefficient constant. Those are some vocabulary terms that we want to be familiar with. So if we come across them, they don't throw us off, right? And a good way to remember coefficient is that the prefix co means together, right? So 4 goes together with the x, right? I'm going to go ahead unless somebody says they need more time. Okay. Oh, I thought it was going to be me. So let's go ahead and take a look at, still talking about algebra. I kind of want to just talk about what's the main point of algebra, or some main things that we need to remember. All we're trying to do in algebra is to get the variable by itself, so we know what it equals, okay? And the golden rule of algebra, you guys have heard me say it probably 100 times if you've been in class from the beginning, is whatever we do to one side, do to the other. Whatever we do to one side, we have to do to the other, right? Okay, those are sort of the big points that we want to understand. We want to get the variable by itself so we know what it is equal to. And then whatever we do to one side, we have to do to the other side. So let's just take a look at an example. And I'm going to start off with a real simple example for those of us if we are new. Something like x plus 3 equals 8, right? We talked about steps earlier in the year. Step 1 is to ask ourselves, what operation, right, is happening? What is the operation? And here we see that the operation is addition, right? And so then we ask ourselves, right, this is a 2 in a parenthesis. What is the opposite of that operation? And in this case, it's going to be subtraction is the opposite of addition, right? And so we're going to go ahead and subtract 3 from both sides to get x all by itself. Remember, that's the main point. So I draw a line down the equal sign so that I know whatever I do to one side, I have to do to the other. Subtract 3, right? 3, a positive 3 and a minus 3, that just equals 0, so it essentially cancels out, right? And if I do it to one side, I have to do it to the other. What's left on this side is just x equals, right? We know what x equals. It equals 8 minus 3, which is 5, right? And you would have known that just by looking at the problem. What number plus 3 is 8? 5, right? We know that. But when they get more complicated, we want to have that process right here. What operation's happening? Let's do the opposite. And we make sure we do it to both sides of the equation, right? Make sure we do it to both sides of the equation. All right, so let's look at an example that's a little bit more challenging. Or maybe, yeah, let's look at one that's more challenging. Like, so this we'll call example B for algebra. This is a two-step equation because we have two operations that are happening, right? If we think about our steps, what operations are happening? Here we have multiplication happening, 4 times x, right? And then here we have subtraction happening, okay? And when we have two operations, the golden rule for when we have two operations is to start with addition or subtraction, right? Because that way we don't make it any harder than it has to be. If we start with the division or the multiplication, it's going to be a little bit more complicated. So for this problem, we're going to do what we always do and draw a line down our equal sign, right? We see what operations are happening, multiplication and subtraction. We know to start with the addition or subtraction, so we're going to focus here first, right? It's subtracting 4, so we do the opposite, which is adding 4. And the golden rule, right? If I do it to one side, I have to do it to the other. A minus 4 and a plus 4 will cancel out. 12 plus 4 is 16 equals 4 times x, right? 4x means 4 times x. So in this case, right, now we're down to one operation, just multiplication. 4 times what number? Equals 16. That's what that's saying, right? The process to figure that out is to do the opposite of multiplication, which is divide by 4. 4 divided by 4 is just 1. So we just have one x left on this side, right? But if I divide by 4 on the left, I have to also divide by 4 on the right. 4 goes into 16 4 times, right? Doing good? Are there any questions about the algebra section before I go ahead and move on? Or is there anything else you want to see? Okay, I count to 10 in my head every time I ask you a question, so I give you that time. Just in case. All right, so let's go ahead and move on. Then our second section that we touched on in the class was prime factorization and greatest common factor. Okay, so when we learned about prime factorization, we learned that all numbers can be broken down into prime factors. So let's talk about, again, let's start with a little bit of vocab. Okay. One of the words we need to know is, what does factor mean? Right? Another word we might want to know is, what is a prime number versus a composite number? This one's a little more important, but so a factor, basically what we need to know about a factor is that it's a number that goes into another number. So for example, I'll write that down. A number that evenly goes into another. So an example of this would be if we have the number 12, I know that 2 is a factor of 12 because 2 goes into 12 evenly, right? So 2 would be a factor of 12 because it's a number that goes evenly into 12, okay? There's certain numbers that are prime because they only have one factor. Oh, question, yeah.
Just so it's only even numbers? If the whole number is an even number, what divides into that number?
Yeah, so only numbers that go into it evenly. So for 12, for example, so what are all the factors of 12? Well, we know all numbers are divisible by 1 and itself, right? So 1 and 12 are both factors of 12 because 12 divided by 1 is 12. 12 divided by 12 is 1. So any number that goes into 12 evenly. 2 goes into 12 evenly. How many times? 6. So 6 also goes into 12 evenly because 6 times 2 is 12, right? A number like 5, however, count by 5 and you skip 12, right? 5, 10, 15. So 5 does not go evenly into 12. Your answer would be like 2.4. That's not what we want. We want only numbers that go evenly, like number 3, right? 3 goes evenly into 12. 3, 6, 9, 12. And so does 4, right? 4, 8, 12. So what I just did right here is I listed all the factors of 12. All the numbers that go evenly into 12 are right here. 12 is an example of a composite number. Why? Because it has more than 2 factors. You're on the right track. A prime number has only 2 factors, and those factors are 1 and itself. So in red, I'm going to give you an example of what I mean by that. 1 and itself, right? Well, that, like the number 7, what divides evenly into 7? 1. 7 divided by 1 is 7, right? Also, 7. 7 divided by 7 is 1. But there's no other number that evenly divides into it. So the only factors of 7 are 1 and itself, right? 1 and 7 itself. So that makes 7 a prime number because its only factors are 1 in itself. Okay? Any questions about that or about that vocabulary? Great. So we talked about prime factorization. Prime factorization. And that means that every number in the world can be broken down into prime numbers that are factors of that number. So let's just look at an example of prime factorization with the number 44. What we learned is that we can break 44 down into prime numbers. And we do that by making a factor tree. So we ask ourselves, what's a number, any number, that goes into 44? We know that 44 is an even number, right? So we know that 2 goes into it, right? And then to find this number, if you recall, to find that second number, what we do is say 44 divided by 2. 44 divided by 2 gives us this number. Okay, and what would be 44 divided by 2? 22. So what this again says is that 22 times 2 also is 44, right? 22 times 2 is 44. So these are both numbers that evenly go into 44. 2, we stop at because it's a prime number. If I were to continue factoring 2, all that would happen is I'd go 2, 1, 2, 1, right? 2 times 1. I'd go on forever like that because the only factors of 2 are 1 and itself, right? It's a prime number. So we stop there, we circle it, this tree stops growing. 22 is an even number again, so we know 2 goes into it. Okay? How do I find the number that it pairs with? That's a square. Don't circle it. Don't even actually, just don't do what I just did. That was confusing. Just leave it by itself. But how do I find that number? 22 divided by 2 would give you this number. 11. And so we break it down into a prime number here. And is 11 a prime number? Yes, it is. It's only divisible by 1 and 11. So now I've broken 44 down into its prime factors. So I have the prime factorization. We write out the prime factorization from smallest number to largest number. And we have multiplication signs because what happens is when we do 2 times 11, what would we get? We would get 44. And that's the golden, that's literally like the really cool theory of math telling us that every number can be broken down into prime factors. And when we multiply them together, we get that number. Any number in the world. So a cool rule or law of math. So why or when would we use this would be the next question, right? And so one of the things that we learned is that you can use prime factorization to, so we're still talking about prime factorization. You can use prime factorization to simplify a fraction, right? So if you had the fraction 177 over 222, we could simplify this fraction using prime factorization. We'd have to do a factor tree for each number, right? I know that by looking at the number 177, I know within a matter of seconds that it's divisible by 3. So we learned a rule that told us if a number is divisible by 3. And that rule is you add up the digits. So in this case, 1 plus 7 plus 7. We get 15. And then we ask ourselves, is the sum, this answer, divisible by 3? And the answer here is yes, 3 does go into 15. Why did we do this? Just to see if this number is divisible by 3. We add up the digits, we see what the sum is, and if the sum is divisible by 3, so is this number. So I know 3 is a factor. So then I say 177 divided by 3 in my calculator, or I can do it longhand if I have to, and that's 59, okay? Is 59 a prime number? Yeah? What about 222? What's it divisible by? It's divisible by 2, right? Ends in 2. It's also divisible by 3. Okay? It's also divisible by 6 because it's even and divisible by 3, right? Let's just do 2. 222 divided by 2 is 111 prime. 111 is divisible by 3 because the sum of the digits is 3, which is divisible by 3. And 37. Okay? So we have broken both these numbers down into prime factors. 37 is a prime number. So then what we can do is list out the prime factors of each number, 3 and 59, 2, 3, these are multiplication, and 37. If they have anything in common, we can cancel them out because we're dividing them by each other. So then we'll have 59 divided by 37 times 2, which is 74. And this is a simplified version of this fraction, okay? So if you were given this fraction and your directions were to simplify it, you can do the prime factorization of each number to help you simplify it, okay? If you had a calculator, you probably wouldn't do it this way. You would just type in this fraction in your calculator. But if you didn't, you would do it this way, and you'd have to do some perhaps long division. Okay, how did I get this? Well, these canceled. So on the top was just 59 left, right? But on the bottom, I had 2 numbers left. I had 2 and I had 37. So I had to multiply them together because the prime factorization has you multiply these, right? So that's how I got the final answer. Any questions? Along these lines, we also learned how to find the greatest common factor, right? We're still in section 2, the greatest common factor of a pair of numbers. So if I was given the numbers 12 and 15 and told to find the greatest common factor, what I do is I list all the factors of each number. So 1 and 12 are factors of 12, 2 and 6, 3 and 4 are factors of 12. I always work from outside to the inside because I think, okay, 1 times 12 is 12, 2 times 6 is 12, 3 times 4 is 12. So I kind of have them paired together, right? And then I can also do the same for 15. 1 times 15, 2, no, 2 doesn't go into 15. 3, yeah, 3 times what? 5. Does 4 work? 4, 8, 16, 12, 16. No, it doesn't work. 5 back to 5, right? So we're done. We compare. What do they have in common? They have 3 in common, right? That's the greatest number that they have in common. That's the greatest common factor is 3.
You always choose the highest, right?
We always choose the highest, right? They also have 1 in common. But we don't want to know all the common factors. We want to know the greatest common factor. What's the greatest of all the ones they have in common? 3. Okay? If I know the greatest common factor of a set of numbers, I can also use that when I deal with fractions. So if I had a fraction, 12 over 15, and I know that the greatest common factor is 3, then I can divide the top and the bottom of the fraction. I could divide them both by 3 to simplify it, right? Simplify it. And that would give me 4 over 5. So the simplest way to write 12 over 15 is 4 over 5, and I found that by using the greatest common factor to simplify, okay? Any questions there? Oh, yeah, there's Kodiak and Homer is with us. Yeah. Okay, let's move on then to least common multiple, okay, or LCM. Factoring has to deals with division, whereas multiples deal with multiplication, okay? Multiples are just like counting by a number, right? So the multiples of 2 would be counting by 2. 2, 4, 6, 8, 10, 12, and so on, right? The multiples of 7 would be 7, 14, 21, and so on, right? So you see the difference between multiples and factors. Factors were breaking things down into smaller numbers, right? Whereas multiples were making these numbers larger. So if we want to find the least common multiple, we have to list out the multiples and then see what they have in common. So if I were to keep going, for example, here, if I said, what's that least common multiple of 2 and 7, I'd list out the multiples until I had one that was in common. So far, I don't have any in common, do I? But if I keep going on 2, 10, 12, 14, ding, 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 right? Now I have one in common. I don't have to keep going to see if they have more in common. Why? Because I want the least, the smallest common multiple. So here, the LCM would be equal to 14. The area that we mostly will use least common multiple and greatest common factor is on a word problem that we have to use that tool to solve it. And you'll see that later on when we get into some practice. Any questions on least common multiple? Okay. Scientific notation the other day. We learned that earlier this week, right? Scientific notation. We learned that it has to be in a certain format to be scientific notation. Why do we use scientific notation? We use it to write very big or small numbers. Okay? Sorry about my sloppy handwriting. We use it to write very big or very small numbers, especially when they won't fit on our calculator screen. Okay? And they have to be in this format. A times 10 to the, we'll call it B. Okay. And this is what we learned the other day, if you were with us. This B is called an exponent. When we have that, it's an exponent. Okay? The 10 in scientific notation, we call the base. And we're going to see a repeat vocab word in scientific notation. This letter A we call coefficient. A has to be greater than 1, but also less than 10. So A has to be between 1 and 10. Okay. And B, our exponent, right here, this is B, right? Always has to be a positive or negative whole number.
Hey, Jeff.
Yeah.
Somebody just made a point that it could be equal to 1, couldn't it?
Great point. Yes. Great point. It could be equal to 1. Good. A can be equal to 1. Thanks, Michelle. B has to be a positive or negative whole number. I like to talk about examples, right, versus non-examples of what that means. -2 is a whole number, whereas -2.5 is not a whole number. It has a decimal. Like 1/4 is a non-example because it's not a whole number. It's part of a whole. Okay? Or 1 1/4, right? It has to be a nice whole number like that for our exponent. Okay, and the base, like here, right, number 10, it's always 10. That's why I just wrote 10. The base is always 10. Okay, so let's go ahead and just look at why and how we use this, right? So if I have this number, go ahead and write this number down. We'll call it example 1 or just example, right? 8, 720, then we'll do 6 zeros. Okay, this would be 100,000, this would be 100 million. So this is 8,720,000,000. When I write in scientific notation, if I have a very large number like this, the first step, step 1, is to move the decimal behind the first digit. Move the decimal behind the first digit. When there's an invisible decimal, like here, we know it's here. It's at the end of the problem, okay? So I have to move it to behind the first digit. This is the first digit right there. Okay? So I'm gonna go ahead and move it. I like to move by 3s when I can, when it's easy. 3, 6, 9. Okay? I just skipped a step because I'm gonna write it sort of in a weird space, not below it. Step 2 is to count how many spaces you moved, right? What did we move? 3, right? 6, 9 total, right? So I'm going to write that new number, 8.72, and my third step, which I just completed, is to drop the zeros. Drop the zeros. We don't need those anymore. So I just wrote 8.72, right? This is my A. Remember? A times 10 to the B. It's always going to be times 10, and B is the number of spaces we moved. B is the number of spaces we moved. So how many spaces did we move? 9. Okay. And so this is the answer. And if we just said write that number in scientific notation, there it is. Okay. What if we had a very small number though? Like, oops, sorry about that. 1, 2, 3, 4, 5, 6 zeros, and we'll say 2, 4. Okay. My steps are essentially the same. There's going to be one minor difference in this, okay? We're still going to put the decimal after the first digit, but it's going to be after the first non-zero digit. So the decimal goes after the first non-zero digit. That, in this case, is going to be 2. So I'm going to move the decimal here, okay, after the first non-zero digit. So I'm going to write 2.4, and I again drop the zeros. This time they're in front of it, right? But I drop those zeros. This is my A, again, times 10 to the B. And B in this case is going to be the number of spaces we moved, right? Except this time it will be a negative. So when it's a very small number, when it's a decimal, when we're dealing with a decimal or a very small number, the exponent will be negative because we're moving it in the opposite direction. So there has to be a reason why we move in the opposite direction, right? We have to tell ourselves that we're moving in the opposite direction. And by doing that, we show ourselves with the negative. So how many spaces did we move? 1, 2, 3, 4, 5, 6, 7. So that would be 2.4 times 10 to the negative 7. So if you see a number with a negative exponent, you know it's a very small number because we've moved the decimal left, right? Whereas if it's positive, we're going to move the decimal right and make it a larger, right, natural number. Okay, questions there? Awesome. Last topic that we just learned about yesterday is inequalities. Inequalities deal with, so we're on section 5. Inequalities deal with these signs, right? Greater than, less than, greater than or equal to, less than or equal to. One of the big things we learned yesterday is that when we graph these on a number line, if it doesn't have an equal to sign, we have to graph it with an open circle, right? If it does have an equal to sign, when we put it on a number line, we have to use a closed circle. So if we had something like x is greater than 3, okay? If we had that and we had to put it on a number line, where this is 0 and 1, 2, 3, it's greater than 3, so it's not equal to 3. So I'm just going to put an open circle to represent that it's not equal to 3. And then I will draw a line towards greater than 3, which is this way, right? And I'd put an arrow signifying that it goes on forever. And that's how I'd graph it. X is greater than 3, not equal to though. If it was equal to, I would shade it in, right? X is less than or equal to 1. Would be, okay, 0, 1. I find 1. This time it's less than or equal to, so I'm going to shade it in to show that it can be equal to 1, and all numbers less, which would be this way, right? X is less than or equal to 1. Okay? That's the basics of graphing it. Just going to give a couple seconds to catch up in case you're writing those graphs down. We also dealt with not just graphing. Where did I go? Not just graphing, but also solving equations that are linear inequalities, not linear, solving inequalities with variables, and it looks something like this, like x, or we'll say 3x plus 4 is greater than or equal to 13. Right? So instead of an equal sign, now we have an inequality sign in the middle. No problem. We do the same thing that we did with algebra. We focus on the addition and subtraction first. Subtract 4 from both sides. That would be 9 now, greater than or equal to 3 times x. Since we have multiplication, we divide both sides by 3. And in this case, x would be greater than or equal to 3. And we could graph that if we were asked to. The one key difference that we learned is if we have, for example, negative, so this will be example 1, that if you want to write that down. This will be example 2. negative 3x is less than 12, let's say. If we multiply or divide by a negative, we have to flip this sign. So in order to solve this problem, I have to divide by a negative 3, right? Both sides are going to be divided by a negative 3. So this sign that was less than becomes greater than. It flips when we divide by or multiply by a negative. So I'm just left with x over here. And here we have a positive divided by a negative. And that gives us a negative. We're not going to go into integer rules today, but a positive divided by a negative is a negative. And 12 divided by 3 is 4. So that would be our answer for this problem. Key is to flip the sign when we multiply or divide by a negative. Okay, if there's no questions about any of those 5 sections or anything else that you want to see related to that, what I want to do now is to give you guys some time to jump into some of the problems. So I gave on this handout GED type questions, okay, that relate to these first 5 topics that we learned in the class. And so these questions would be something that I would expect to see on the GED. It would be these topics, but geared up a little bit, perhaps. Put into a word problem or put into a geometry problem, right? So they're not going to often give you on the GED a straight up question like 3x plus 4 equals 12, for example. They might give you that, but they're more often going to give you a multi-part question that involves a little bit more. And so that's what this handout gives you. Okay, so I am going to just kind of hang on the line while everybody works, and then I'll be available for questions and to go over answers. And I am happy to stay past 12 if necessary. I'm going to stop the recording at this point, or pause it, come back. So we're going to look at number 1, and let's see. So for number 1, Bill and Lou are in different physics classes, right? And Bill's teacher is going to give him exams with 30 questions on them. So Bill, oh, I don't like that. I'm going to jump into PowerPoint. Okay. Sorry. Sorry about the delay. 1 sec. Okay. So we have Bill, who is going to take exams, right? And on every exam, he's going to have 30 questions. We have Lou, and on his exams, there's going to be 24, right? But their teachers say at the end of the class, no matter what class you're in, you're going to have the same total number of exam questions at the end of the year, right? And so this is going to end up being a LCM question, least common multiple, because we're going to say, okay, there's Bill, his first test, 30 questions, right? And then after he takes the next test, it will be 60, right? Take another one, 90, and another one, 120. Okay, Lou, after his first test, he's going to be at 24, right? And then after a second one, 48. Then 72, right? And so on until we get to this point right here. So after Lou takes 5 tests and Bill takes 4, they'll have the same number of questions completed, 120, okay? And so that would be the answer. What's the minimum number of exam questions Bill and Lou can expect in their class? Well, a minimum of 120, because they're always going to be in this increment, and that's the first time that they match up, right? And have the same number. So a minimum of 120 questions. So this problem doesn't ever tell you use least common multiple to find the answer, right? You just have to know from practice, right? And from pulling that out of your toolbox because you learned how to do it, how to use it. Oops. Any questions on that? Okay, let's look at number 2. Oh, question?
Yeah, is that the quickest way you can do that one? Because let's say he had, you know, a different number, we would just go. We were discussing if that's the quickest way or not.
Did you guys think of another way that you might do it?
We don't have another way, but if it was an astronomical number, you know, some big number, we were just.
Yeah, I don't know of another way, but I also think that if they gave you that type of question, they'll probably want you to use, you know, like LCM or listing the multiples, so they'll probably make it a manageable number. That would be my thought. But it's a good thing to think about. But I don't know of another way, but if you guys find one, share it with us too. So let's go ahead and jump in number 2. Number 2, we have the rectangle, right? We have 4x plus 8 on one side and 2x plus 3 on the other. And the first question asks us to find the perimeter in terms of x. So number 1, we have to know, what does perimeter mean, right? And that's something we have to know for the test. You need to know that. And perimeter means we add up all the sides of whatever shape it is. Doesn't matter what the shape is, perimeter means all the sides added up, okay? So for this problem, we're gonna have 2x plus 3, right? Plus this other side, which is 4x plus 8, plus this side, which is 2x plus 3, right? These are the same, it's a rectangle. Plus this side. Then we have all 4 sides added up, right? And this side is the same as this one, 4x plus 8. One thing we learned about addition this year is that it's commutative, right? 3 plus 7 is the same as 7 plus 3. Is that correct? So that means I can add in any order. So what I'm going to do myself here is I'm going to rewrite this problem so that all of my like terms are together. Because this and this and this and this can be combined. So I'm going to rewrite it as 2x plus 4x plus 2x plus 4x, whoops, x. And what does that give me? 2x plus 4x is 6x, plus another 6x, right, is 12x. I can also do the same with all of the numbers, the constants here, and say, okay, 3 plus 8 plus 3 plus 8. And that's going to be 22, right? So I'm going to have 12x plus 22. So perimeter is equal to 12x plus 22. I just add up all the sides and then combine the similar terms. The x's can all be combined and the numbers can all be combined. And then I can move on to step B. Rather than plugging 4 in and adding up every side, well, I know I have a formula for perimeter, right? So B, they want to know what's the perimeter if x equals 4. So I'm just going to say, well, 12. If x equals 4, that's 12 times 4, right? Plus 22. So that's going to be 48 plus 22, right? And I can do that in my head because I could add by 10 twice. I'm going to do it, right? 48 plus 10 plus 10 plus 2. That's how I do it in my head. Okay? 48, 58, 68 plus 2 is 70. Okay? So for mental math, it helps if you break it into increments of 10, right? So that's going to be 70, the perimeter. So I added 20. This is 22, right? I added 22 to 48. Any questions on that one, Kodiak or Genoites? Homer's not listening to us. They're doing their own thing.
Yeah, questions. That's good. Thanks.
Good? Okay. So I'm going to go ahead and pause the recording again, and then we'll jump back when we're ready to go over 3 and 4, perhaps. Or Kodiak, when you're done with 3, we could say, let's go over 3. Just let me know how you want to do it. So number 3, Michelle manages ordering for a hospital. She bought one package that had 21 vials of vaccine, okay? And she also bought one package of, so I'm just going to call this, she bought 21 vials of vaccine, right? And she has one pack of 30 syringes. She wants to use all the supplies and organize them into identical sets and place them in containers. What is the greatest number of identical sets Michelle can make? Or how many containers can she put together? Would have been another way this could have been asked, right? And so she's at the hospital, right? She has her 30 syringes, her 21 vaccines, little vials, right? And she wants to put them into little packages. So she's going to divide them up, right? She's not going to multiply them, right? She's going to divide them up because she only has 21. She's got to divide them up. But she wants to have an equal number of each kind, right? Each kind. So what kind of problem is this? It's greatest common factor. Why factor? When we factor something, we divide it up, right, in 2 parts. So if I find the greatest common factor, that's going to tell me how I can break it up so that I use them all evenly, okay? And so I can list all the factors of 21 and 30, or I can do a factor tree. So why don't I just list all the multiples, right? You can do it either way, but I'm going to say, okay, 21, all the factors, 1 and 21. Does 2 go into 21? No. Does 3? Yeah. 3 goes into 21 how many times? 7. 3 times 7. Does 4? Nope. Does 5? Nope. Does 6? Nope. Does 7? I'm back to 7, so I can stop. 30. 1 and 30. 2 and 15. 2 times 15 is 30. 3 times 10. 4, no. 5 and 6. And I'm done. So now I want to know what is the greatest common factor here? And it's 3. So what does that mean in terms of our problem? That means we could have 3 identical sets. So Michelle is going to take 3 containers, okay? And we're going to use all our supplies and put an equal number in those containers, right? And so let's think about how many vials of vaccine is going to go in here? 7 in each one. 7, 14, 21. We used them all, right? What about syringes? 10, right? Because 3 and 10, 3 and 7, right? So 10 syringes, 10 syringes, 10 syringes. So we used 30 syringes, we used 7 vaccines, and we made 1, 2, 3, right? Packages. And we used them all up, and they're identical, right? So we did what they asked. But the hardest part of the problem is figuring out what tool in my toolbox do I have to use? Its greatest common factor. When we talk about dividing things out into identical or packages that are the same, right? So you might want to write that down in your section about greatest common factor, right? We're dividing out, or if we're making same / identical packages of some kind, it's going to be a greatest common factor problem. Draw a picture if you can to help you think it out, right? Does it make sense? Like I tried greatest common factor, I found 3, and then I drew a picture to kind of think it out. What does that look like? What does that mean? Am I right? And it makes sense once I did that, right? Any questions on 3? Okay. Kodiak, did you want to jump right into 4, or do you guys need some time to look at that one? Number 4. Number 4 says, Carrie is using a rectangular piece of plywood. I would stop right there if I was doing this problem. Why? I'm going to draw a rectangle. Exactly. They said she's using a rectangular piece of wood, so I'm going to stop right away and just draw a rectangle. There we go. He wants the area of a workbench to be at least 100 square feet. So the area is this part right here. So he wants the area to equal 100 square feet. The length of the plywood is 25 feet. So we have the length, but they don't give us anything about a width. Usually when we talk about rectangles or a square, we think of it as length and width. Okay, so if they give us the length, we don't have the width, right? So which inequality shows the minimum width of the plywood? So this requires a little bit more thinking because we need to know what are they dealing with. So the big hint in this problem is this, in any word problem that you get. If they tell you what the area is, you're probably going to use that in some way. They didn't do it for no reason. So we have to think, they gave us the area of a rectangle, but we're missing part. So we should look at our GED formula sheet. And when we do, we're going to see that the area of a rectangle is equal to length times width. So basically, with this, we know that 100, right, is equal to 25 W. But in this case, we want it to be at least 100, right? Didn't they say that in the problem? So we want it to be equal to 100, or we want it to be greater. The area we want it to be, right? We want the area we want the area to be greater than or equal to, right? 100. So when we multiply the length times the width, we want our answer to be 100 or greater, right? So which inequality shows that? I actually put my sign sort of the wrong way, I think here. Sorry. But which one, so if we look at, which ones do we know are not the correct answer? We know that A and B are not correct because they involve addition and subtraction. We're doing area, which has multiplication in it, right? So if we look at C and D, we can try to figure it out from there, right? 25W is less than or equal to 100, or 25W is greater than or equal to 100. We are building a workbench that we need to have at least 100 square feet as our area, right? So this answer, when we do 25 times W, has to be 100 or greater. Does that make sense? It has to be 100 or greater when we multiply them because that gives us our area. So it has to be which answer? D. Because we need W to be something that gives us 100 or larger, okay? So the answer for that would be D. Does that make sense? Kodiak, are you with us?
Yes.
Okay, great. And then part B, what is the minimum width of the plywood if the length, if that should say if the length remains 25 feet, sorry. So then we would basically what part B is telling you to do without telling you is to solve it. It's basically telling you solve this. So 25W is greater or equal to 100. They're asking you to solve that essentially for part B. So I have to do algebra, right? Line down the middle. This is multiply, so I divide both sides by 25. And so the width would have to be greater than or equal to 4. Does that make sense? It does, because if this is 4, 4 times 25 is 100. And now I have my minimum area of 100. Or if it's 5 times 225, that would be 125. And my area would be at least 100, right? So if this is 4 or bigger, my area is going to always be at least 100, if not larger, which is what they said they wanted, right? So if maybe you picked C and you solve for it, but then it wouldn't make sense when you thought about it, because W can't be less than 4. Because if W is 3, then our area is only 75, okay? All right, so let's just move right on then to number 5, which is a scientific notation problem, right? A supercomputer can perform, let's see, what do we got? Million, billion, 50 trillion operations per second. How many operations can the computer perform in 1 hour? So first thing I'm going to do is take 50 trillion and turn it into scientific notation to make it easier to use. So 5.0, right? And then how many times did I have to move the decimal place to get it there? 3, 6, 9, 12, 13, right? So that will be times 10 to the 13th power. Okay, and so that's how many operations can happen per second, right? And they're asking me how many operations can it perform in. So the question is, what about 1 hour? So I have to take this and say, well, what does that equal if I make it an hour? This is just per second. So you have to think about it like this. Okay, 1 second, right? how many seconds are in 1 minute? So there's 60 seconds per minute, right? How many minutes per hour? Also 60, right? 60 seconds in 1 minute, right? And then 60 minutes in 1 hour. So I have to take this number and multiply it by 60 to get it in terms of minutes, and then multiply it by 60 again to get it in terms of 1 hour. And so you have to use your calculator, right? And you have to type in 5.0, and then you have to hit the button that looks like this, times 10 to the n. That's our scientific notation button. And then you type in 13, okay? And then you have to scroll over using that black button at the top right, and multiply by 60, and again, multiply by 60. After 10 to the n, you type in 13 in the exponent. And then you hit over with the black button on your calculator. And then you times 60 times 60. But you have to get out of the exponent first by hitting over. And what do we get? Because you have to convert from seconds to an hour. There's 60 seconds in 1 minute. So this will change it. The first time you multiply it by 60 will be how much in 1 minute. And then the second time you multiply by 60 will tell you, well, there's 60 minutes in an hour. So I multiply by 60 again, and that gives you 1 hour.
I just did, can you, well, it looks like it worked. I just did 60 multiplied by 60 to get the exact amount of seconds, and then do that 5.0.
Yeah. Same thing.
By 10.
You did the same thing, you just did it from right to left, right? So same thing, it works either way, because we can do multiplication in any order, right? Okay, so that would be number 5. And what was the answer there? It was, what did 1.8 times 10 to the 17th. So that's how many operations it can do in 1 hour. So that would be, I might want to label it operations, right? That's how many operations it can do in 1 hour. A whole lot. Okay. And then lastly, let's go over the challenge question. This is a hard question. But you get questions that are similar to this on the GED. I feel like this is even harder than what would be on the GED, but you get questions that are similar where you have to figure out missing sides based on the information that was given to you. Sorry about my ugly drawing. You're gonna have to deal with it for the next couple months. Okay, so they give us a bunch of info. 4, right? 3a plus 4, 2a. And this whole side is 6. Their first question is, what is the perimeter? So again, we have to add up all the sides. The only problem is they didn't give us every single side, right? We are missing this side and this side. But they gave us enough information to know what those sides are. We just have to figure it out. So what you have to recognize here is that they gave you what this side, right? This whole side, we know what it equals, right? So imagine if we move that down, that would be the same, right? It would be this long, right? And we know how much it is from here to here. It's 2a. So in order to find this, I have to take the length of this side and take away 2a. So this side right here is going to be equal to 3a plus 4 take away 2a. So it's going to equal a plus 4. This side, right? That's tough, but we can figure it out. So this side here is a plus 4. What about this side? Same deal. We know the length all the way from top to the bottom because over here it's 6. We know the length from here to here is 4. So this side right here, that side is going to be 6, this whole length, minus the other part right here, from here to here is 4. So how do I get this to be 6? 6 minus 4 is 2. So this missing side is 2. Because 2 and 4 would give it the full 6. Okay, and we did this. I should have done that side first because it's easier to understand with numbers versus the variables. Sorry about that. So now I have all the sides. Okay, they will never give you a problem that you can't solve. You might look at that originally and be like, I don't have all the information I need, but you do. You just got to really look and try to figure it out. So now for perimeter, 3a plus 4, right? So we're going to add up all the sides, plus 6 plus this side, 2a plus 2 plus a plus 4 plus our last side, which is 4. And then I'm going to combine like terms. 3a plus 2a is 5a, plus 1 more a is 6a. And then 4 plus 6 is 10. Plus 2 is 12. Plus 4 is 16. Plus 4 is 20. So in terms of a, the perimeter is 6a plus 20 of this whole ugly shape. Then they asked me for part B, what is the area? So for part B, we have to find the area of this shape. And in order to do that, we have to break it into 2 separate shapes and then add them together. So what do we have here? We have like a rectangle, right? And another right here. So if I think about it like that, I have this shape plus the shape that breaks off of it, right? So I have a shape like this. And then this one, this shape. So this first shape, I'm going to break out right here. The one side is 4, and the other side is 3a plus 4. This other shape, I'm going to draw right here. We have one side that is 2a, and we have the other side that is 2. And to find the area of a rectangle, I multiply one side by the other. And so that's what I'm going to do here. 4, this is hard, times 3a plus 4, times the whole thing. So what we have to do is use parentheses like this. 4 times the whole quantity of 3a plus 4. And so this is called distributive property. That's why I made this a challenge question, because it has a lot of things and things we haven't talked about. So we're going to do 4 times 3a and also 4 times 4. Like that, we distribute it into the parentheses. 4 times 3a is 12a. 4 times 4 is positive 16. So the area of this first one is 12a plus 16. What about the second one? Well, it's just 2, this one, 2 times 2a, one side times the other. 2 times 2a. 2 times 2 is 4, so we have 4a. So the area of this one is 4A. We need to know the area of the whole thing, so we have to add them together. 12A plus 4A plus 16. Well, we add up the A's, right? 16A plus 16. And then there's a part C, right? What is the area and perimeter if the shape is A equals of the shape if A equals 2? So that's our last part of the question, right? So if A equals 2, what is the area? What is the perimeter? Well, what do? We have to plug in to our formulas, right? This we found right here was the area formula. So we plug 2 in, and that gives us the area. 16 times 2 plus 16. Right? And that's going to be 48. For area. And perimeter, here's our formula, right? 6 times, we plug in 2 because they told us A equals 2, plus 20. So perimeter equals 32. You will probably get a problem on the GED that's similar to this, but not quite as hard. Similar in that you have to find out what the missing sides are. They probably won't give you variables. You'll probably have to do like this, where you had to figure out, okay, this side's 4, so this side's 2. You're very likely to see a problem like that. No. The great part about the GED is that you don't have to get every question right in order to pass. Okay? You have to get like 70% basically. Okay? Kodiak, Homer, any questions?